Thank you very much, Dr. Wang, for your nice introduction. So my name is Weina, and I'm an assistant professor from Stevens Institute of Technology, and Dr. Kamal Kayat is my PhD advisor. So the work that I'm going to talk about today is actually a review paper that we worked together, which published on cement and concrete research. So this paper actually covers a lot of aspects of rheological properties of UHPC, such as the flow models, the rheological measurements techniques, the effect of various raw materials on the rheological properties of UHPC, and also the rheological properties requirements and strategies to control the rheology of UHPC for different applications. So in the interest of time, I could not cover all these things. So today, I will only focus on the UHPC with adapted rheology for different applications. So for better fiber distribution, for slope casting, and for ease of large-scale production. So first of all, I will introduce the rheology control for better fiber distribution. But why it is important? Because the better oriented fibers lead to greater flexural performance. So as you can see this figure, so the UHPC with 1% well-oriented steel fibers can show like even better flexural performance than the UHPC with 2% steel fibers without well-oriented. So at the same amount of steel fibers, as you can see, when you like well-oriented the fibers, the flexural properties is significantly improved. So this is one thing. And also, most currently, we did some research on the corrosion of UHPC. So we found when the fibers are well-oriented along the steel bar direction, as there's no contact between the steel fibers and steel bar, so the two metals are were not electrically connected. So we didn't find any galvanic corrosion. So the better fiber orientation also benefit the corrosion resistance. Let's see. So to achieve the better fiber distribution, for now there's a lot of researchers. They try to improve the casting methods. For example, they place the UHPC along the longitudinal direction using different tools, layer by layers. But also, we could have the self-adaptive fiber orientation in flowing UHPC, which means we need to develop a highly flowable UHPC, and we use in the chute and let it flow from one side to another of the UHPC beams. So during the UHPC flows, the fiber will be reoriented in the shear zone. So where the gradient of the flow velocity will apply a torque to the fibers and orient it to the tensile direction. So the thing is, the gradient of this flow velocity is controlled by the viscosity of the suspending mortar of UHPC. And not only the fiber orientation, but also the fiber dispersion, is also controlled by the viscosity of the suspending mortar. So besides we using the better casting methods, but also we will need to optimize the viscosity of the UHPC suspending mortar for the better fiber orientation and the dispersion. So to test the viscosity of the UHPC suspending mortar, what we did is that we used the contact 6 rheometer, and with very low, relatively low shear rate, up to 20 per second. And we can obtain a linear relationship between the shear stress and shear rate. And then we apply the Bingham model to fit this curve or fit this line and obtain the plastic viscosity as the slope of the line. So to investigate how the plastic viscosity of the UHPC suspending mortar influence the fiber distribution and the flexural properties, we investigated 6 different mixtures. So for these 6 mixtures, we fixed the steel fiber content at 2%. And we also fixed the cementitious materials content and the aggregates content. So the only thing we changed is the dosages of the viscosity modified admixtures, or the VMA. So we investigated 6. So the different dosages of VMA will result in different plus viscosity of the UHPC suspending mortar. So for the experiment, first of all, we need to fix the mini slump flow of the UHPC mortar to around 280 millimeter. And then before we add in fibers, we tested the UHPC mortar for the mini refunnel flow time, and at the same time we tested the plastic viscosity. And we found there's a very good linear relationship between the flow time and the plastic viscosity. And the good thing of it is that we could use this simple tool as an indicator of to evaluate the flow time as an indicator of the plastic viscosity. So once we tested the viscosity of the mortar, we add the 2% fibers to the mortars with different viscosity. And at 28 days, we tested the flexural properties of the beams. And then we cut sections from the fractured beams for the evaluation of the fiber orientation and fiber dispersion. So the whole idea is, so when you add different dosage of VMA to the UHPC mortar, you will have different flow time and different plastic viscosity. And remember that they have a linear relationship. So different viscosity of the suspending mortar will result in different fiber distribution, orientation, and the dispersion. And the different fiber distribution will result in different flexural properties. And eventually, we can establish a relationship between the flow time of the suspending mortar and the flexural properties of the UHPC, so that we can simply control the flow time of the suspending mortar to control the flexural properties of UHPC. So we use the binary images of the cross sections of the beam specimens to evaluate the fiber dispersion and orientation. So as you can see here, with the mixtures with different VMA dosages, the fiber distribution is different. And we use the eta as the fiber orientation coefficient. So when the eta is close to 1, it means the fibers are perfectly aligned along the tensile direction. And we use the alpha as the fiber dispersion coefficient. So when the alpha is equals to 1, it means that the fibers is perfectly uniformly dispersed. So as you can see here in these figures, so even though we use exactly the same amount of steel fibers, 2%, with different VMA dosages, the flexural properties differentiate a lot. So when the VMA dosages equals to 1%, we can have the highest flexural strength and the dissipated energy. So which is calculated as the area under the load and deflection curve. So the reason is that when we add the 1% of the VMA, the viscosity of the suspending mortar leads to the fibers has the relatively high eta values, the orientation coefficient, and lead to the highest dispersion coefficient. And these results tell us that if we can use some admixtures, for example, the VMA, to adjust the suspending mortar of UHPC for the flow time to around 46 seconds, then we add fibers, and then we can obtain the UHPC beams with the highest flexural properties. And we also validated this kind of concept by changing the mixture design. So we changed the binder system, And we controlled the mini funnel flow time of the UHPC mortar to 16 seconds, 68 seconds, which is close to the 46 seconds, which is the optimum flow time. And also we control the mixtures with 93 seconds. So as you can see, the results as expected. When the flow time of the suspending mortar is controlled around 48 seconds, we obtain the highest flexural properties. But it is noteworthy that even though we increase the fiber distribution by increase the VMA, by increase the viscosity of the suspending mortar, we still observed the decrease of the flexural properties. So this is actually because if you add much VMA, if the viscosity of the matrix is too high, a lot of air will be interrupted in, and that will weaken the matrix of the UHPC. And also, as the post-cracking behavior of the UHPC is highly dependent on the bonding behavior, bonding properties between the fibers, the steel fibers, and the matrix. And based on our pull-out testing, we found that if you add 2% VMA, there's too much VMA, the bonding properties between those two are significantly reduced. And this is because more VMA, the higher plastic viscosity of the matrix, and more pores observed between the fiber and the matrix. So we need to find the optimum viscosity of the suspending mortar that will give us a better fiber distribution, but at the same time, it will need to give us a better or a denser microstructure, or better or good microstructure. And also, we conducted some other research on the fiber contents on the rheology control, and we found that for different fiber contents, the optimum viscosity values is different. So the UHPC with overall, the UHPC with higher fiber content requires higher viscosity of the suspending mortar to secure the highest flexural properties. And also, we found there's a significant size effect on the fiber distribution. So as you can see in these figures, okay, so both the fiber dispersion coefficients and the fiber orientation coefficients decrease with the increase of the specimen thickness. But fortunately, if we use the optimum VMA, we can effectively reduce this kind of size effect. So as I mentioned before in our previous slides, that we could use the mini funnel flow time as a simple tool to evaluate the plastic viscosity of the UHPC. But still, you will need to take your sample out of your mixer, and you need to fill the mini funnel and test that. It will still take time. So most currently, we developed a deep learning method to assess the plastic viscosity of UHPC using the video stream. So what it means is that the input of it is the images extracted from the videos taken during the concrete mixing. And after that, the images will send to the feature learning layer. So this one will extract the features based on the pixels of the images inputted. And it will send to the sequence learning layer. So this layer will convert the information from the images to sequential data and send it to the classification. And then the output of it is the plastic viscosity of UHPC. So the whole process, the whole assessment time, including taking the videos, is less than 1 minute. So that will help a lot, or will accelerate this kind of evaluation or assessment viscosity. So if you take a look at the training and validation losses curve, so these results are pretty consistent, which means the model does not overfitting or underfitting. And also for the training and validation accuracy results, as you can see here, those are very close to 1, so which means the model can provide a very good, very high accuracy of the classification. So here is some of the results that we have. So as you can see, the input is some of the images extracted from the videos, and we received a very high accuracy of the prediction. And this method will be promising to be applied for real-time rheology assessment for the quality control if we wanted to use rheology control for better fiber distribution. So another application of UHPC rheology here I want to talk about is the development of thixotropic UHPC as the thin overlay for the bridge deck. So the UHPC normally is developed with self-consolidating properties. So this self-consolidating properties is good when you do the bridge joints casting or the closure casting, and it's good for the casting of a complicated precast element. But it will make it very difficult if you want to cast this kind of UHPC as an inclined surface. On the inclined surface where the crown design with slope is required. So enhancing the UHPC with the thixotropic property can make it easier to be mixed. And also after you cast it on the slope, it will stay still. It will not flow. So you can reshape it into any forms. However, if you take the thixotropy as the slope of the linear relationship between the static yield stress and time, and you will find that the UHPC, the bond strength between the UHPC and the substrate decreases with the increase of thixotropy. And one of the way we can do is to apply some vibration. So vibration can increase the bonding strength. But for the UHPC with different thixotropy, you will need a different vibration time to achieve the optimum bonding strength. And also, if you wanted to shorten this time to reach the optimum bonding strength, then you will need to apply higher vibration energy. So the last application I want to talk about is the rheology control for large-scale UHPC production. So it is reported that the UHPC is very hard to mix at a large volume production or at elevated temperature. So from our preliminary studies obtained from the ICAR rheometer, we found that at the beginning of the mixing stage, when you can see that the mixtures is powder-like, so it's easy to mix. It's easy to mix it because, as you can see, the required mixing torque is low. It's not high. But when the concrete turns out to be clumps, the mixing is getting very hard. It's because, as you can see, the required mixing torque is significantly jumped. And in our case, when the mixing time is 90 seconds after water addition, the mixing torque reached the maximum values. So only when the mixer overcomes this maximum torque, it can keep mixing. And after that, and after the mixer overcomes this maximum torque, the mixing will getting easier and easier. So as you can see, the mixing torque is dropped significantly. So for the UHPC with very large scale, very large volume mixing or at elevated temperature, the required maximum mixing torque is too high, so that the mixer may not have such high mixing capacity that overcome this maximum torque. So that is why some of the mixer will stop working during the mixing. So for different conditions, for example, for the UHPC with different mixture design, with different volumes, or at mixing at different ambient temperatures, we may need to use different mixing procedures. So for example, if you have a mixer with the capacity of mixing torque around 20, okay? So if you mix all your mixtures or all your raw materials and the liquid at the same time, or you add the water first and then add all the raw materials to this liquid, the mixer might stop working because the mixing torque, as you can see, is more than 50, which exceeds the mixing capacity of the mixer. But if you reduce or divide the whole raw materials into 3, which means you homogenize 1/3 of the raw materials first, and then when it gets well homogenized, and then you add the second part and the third part, as you can see, you can significantly reduce the maximum torque. And if you have the small mixing capacity mixer, you can still mix it. But this kind of method, it will prolong the total mixing time. But from our preliminary results, it shows that the fresh properties of workability and the hardened properties was not significantly influenced. So this is a possible way to reduce the maximum mixing torque and for the ease of large-scale production. And that is all for my presentation today. And thank you very much for your attention. I would like to take any questions if you have. Thank you.
Thank you, Weina, for the very interesting presentation. And we do have at least one question on the Q&A box and another one in the chat. On the Q&A box, we found that would you please verify which fiber orientation result in no galvanic action? Random orientation of parallel to the rebar. You can see that question in the Q&A.
Yes, I saw that. Yeah. Thanks for the question. I just go back to the slide. So the thing is, the steel bar, if it's not well coated. So if we have different types of steel fibers, actually, some is grass coated, some is zinc coated. So this metals is actually different. So if you didn't well orient it, if the fibers contact the steel bar, so there's 2 kinds of metals. So when it's electrically connected, there will be galvanic corrosion there. So this is why it is recommended that when we cast this kind of specimens or structural elements, it's better to well orient the fibers.
Then I have another following up. Do you consider using deforming agent?
So in our mixtures, we actually add some of we call it air detrainer mixtures. It's a kind of a deformer. So it's better to reduce the air content using that if you wanted to have lower air content in your mixture.
Okay, here is the last one. If anybody have further question, you may put on the Q&A box or chat, then Weina will reply to you. But this one is on slide 11, number 11. what is the difference for first crack between all the different VMA dosages?
11.
Yeah. This question is in the chat.
In the chat? Let me see.
Yeah.
I'm sorry.
Yeah.
For slide 11, what is difference for first crack between at all difference? So the first cracking we observed is almost the same. So when you have the same amount of the steel fibers, when you have almost the same matrix, the first crack is almost the same. Is what we observed. So for overlay slide 22, did you look at different substrate surface to determine the bond performance? Let me see. So for 22, so for this one, actually we didn't treat in different. We just do some sandblasting. But in the future, definitely we will do some other treatment to see how it influenced the bonding strength. Thank you very much for your question.
Great. Thank you very much for excellent presentation.